want to teach another class that is not physics, I'm okay with that. At this point, it's like okay, so a couple of things. There's gonna be homework due this Friday. There's gonna be a new homework on Friday to do next week. And your next exam is gonna be what would say Emma? The 30th. It's gonna be October 30th. So we still have 3 weeks. So plenty of time. So what I want to do today is we're gonna do a couple of problems involving impulse momentum, and then we go to the first conservation law. There's the conservation of momentum. The problems that we're gonna be doing with impulse momentum, they're gonna be kind of simple. We need a little more equations. We need a little more tools to be able to do problems a little more complicated. So we're gonna see conservation of momentum. Then we see collisions and conservation of energy, and then we're gonna go back again to impulse momentum. So we're gonna go a little bit round trip. Okay. Okay, so the first problem, we're gonna assume that I have a mass of 3 kilograms. And this mass is gonna experience a couple of collisions or a couple of impulses. And I'm not sure, oh, sorry. I got it. Give me a minute. There you go. There you go. Can you see it now? I hope you can. Oh, now. Perfect. There you go. I hope everybody can see the paper now. So we have a mass of 3 kilograms. There are going to be a couple of impulses. There were a couple of people hitting or bounces or whatever. And the graph that describes those interactions is going to have this shape. So, I'm going to say this is 2, this is 6, this is 10. This is time in milliseconds. Minus 1,000. This is 1,500. And the force is in newtons. Okay, so that's the graph of impulse. What I want to know is what is the net impulse. Okay, now you can imagine that you can divide this impulse, this total impulse, you can divide it in 2 sections, section 1 and section 2, and then the net impulse will be the sum of the 2 sections. Okay, this impulse for section number 1 is going to be positive because the forces are positive. For number 2, the impulse is going to be negative just because the forces are going to be negative. Okay, so you start to calculate that impulse, that net impulse, and then just review really quick. while I drink my tea, like if I were 80 years old. Cooper, are you there? Can you open your camera?
Yeah, I'm here.
Can you show me your camera? I have no idea who you are.
Can you see me?
Nope.
Can you see me?
Give me a minute. Nope, I cannot see you. I have no idea who you are. You need to send me a picture or something.
Yeah.
Okay. I have no idea. Check the time from 2 seconds to 6 seconds. Hold on a second. Cost is cost as 3. We just want the impulse.
Okay.
You can calculate that from the graph. The time is 10 seconds. So it will be 4 times 10 to the 3. Yeah, so the time is in milliseconds, so this will be 4 times 10 to the 3. Okay, so so what I'm gonna do basically is just add the areas under the curve. So the impulse for the first section is gonna be the area under this curve, and because the curve has the shape of a triangle, then the impulse for the first section is gonna be 1/2 of the time times the maximum force. So this will be 1/2. The time is 4 milliseconds, so that will be 4 times 10 to the minus 3. And the maximum force is the 1500 newtons. Kennedy, what you got?
I don't know. I used the wrong number.
Oh,
Yeah.
Mary. 3. So it's 3 Newton seconds. Okay, so that will be the impulse of the first section. For the second part, for the second section, well, now the shape is a rectangle, so that's just based on height. So this will be, the base will be, or so will be times the force. That will be 4 milliseconds multiplied by 1,000, negative 1,000. So that will give you 4, negative 4. -4 Newton second. So you add the two together. And that will give me -1 Newton second. Yes.
Where did you get like the 4 times 10 to the -3?
So we know from the graph that the first section goes from 2 milliseconds to 6 milliseconds. So delta t, the time that the impact lasts or the impulse lasts, is going to be 4 milliseconds. And for the second section, it's going to be goes from 6 to 10. So that's another 4 milliseconds. Okay, so this is the impulse. And we know that impulse is also the change in momentum. So the change in momentum is also going to be -1 Newton second. We don't know what is the initial or final velocity. We can calculate what is delta V. So we know that the change in momentum is mass times delta V. We have the mass, we have the change in momentum. So we can calculate the change in velocity. We not be able to know precisely what is the initial and final velocity. So I'm just going to do it really quick. Delta V will be delta P over M. This will be -1 Newton second over 3. So that's going to be -0.33 meters per second. Okay, so this is delta V. So this is not an absolute change. This is not. We don't know what is the initial and what is the final velocity. What we know is that we know that delta V is final minus initial. We know that the initial is going to be bigger than the final velocity. That's the only thing that we know. We know that this subtraction is going to give us -0.33 meters per second, but we don't know specifically what value of final or what specific value of initial we're going to have. We just know this this relationship, that the subtraction of the difference between the two of those is going to be -0.33. Okay. Make sense? Okay. So a different kind of problem. I'm going to have a mass of 600 grams. And now I'm going to have a graph of time versus force. And this is going to be in seconds. This is going to be in newtons. No, sorry. Time versus velocity. And the velocity is going to be in meters per second. And the graph of velocity is going to look something like this. So this is -3.0, and this will be 3.0. Okay. So you can imagine that you have this mass. You are throwing this mass through a spring. The spring is going to compress. It's going to, and as the spring compresses, the velocity of the mass is going to become slower and slower and slower. Eventually, the mass compresses to a maximum value, and then it's going to start stretching. And as the spring stretches, it's going to be pushing your object to the opposite direction. So what we have here is that it's moving towards the left at a velocity of 3 meters per second, and then goes through a velocity of 0 right here, and then it's going to be moving to the right at a velocity of 3.0 meters per second. Okay, so these give you the initial velocity and the final velocity. And the impulse of this spring, of this object, is going to look like this. Okay, it's gonna look like that. It's gonna look like a triangle. The maximum force that we're gonna have is 36 newtons. And what we want to find out is what is delta T. What is the amount of time that you apply in that force? So when we look at the impulse momentum equation, remember that we have two parts. We have the impulse on one side and we have momentum on the other one. This part of the equation, you get it from that graph. This part of the equation, you can get it from that graph. Kaylia, are you not supposed to be on Wednesdays here?
I am supposed to be in class on Wednesday, but I have lab today and I thought I would eat lunch before, so I'm making food.
Ah. So where would be the final velocity? On the initial velocity?
Yeah.
And you have the mass. So you have all the values here, right? So what would be the maximum velocity? The maximum force?
Yeah.
Mhm.
So let's put those into there.
That's it. Plug and check. That's how I'm going to just describe my class. What do you got? 259 seconds?
Yeah, that's not it.
No. So this is like multiplying by 2. So it's 2 times 3.6 over 36. I think you did it. Yeah. So I can explain to you, but you basically divide 3.6 over 0.5, and all of that you multiply by 36. So just be careful. Oh, I see. Yeah, that's good. Awesome. 600 grams.
I think so. Oh, no problem.
So, so this one gives you the initial velocity, and it's gonna give you the final velocity. So if you don't care what happens in the middle, the only thing that you care is what is the initial velocity and what is the final velocity. So with that, you can look at your momentum equations, and that's the one that you use. And remember to change this to kilograms. So 600 grams will be 0.6. You don't see my face, but I like to wow. There you go. Okay, so really quick. So from these graphs, when we're working with momentums, we really don't care what's going on in the middle of initial and final states. The only thing that we care is what is the initial velocity and what is the final velocity. So to calculate delta P, well, the only is just the final momentum minus the initial momentum. And this will be the 600 grams and multiplied by the final velocity, that is 3 meters per second. And here the initial velocity will be negative 3.0 meters per second. The impulse, the right side of the left side of the equation, because we're working with a graph that looks like a triangle, the impulse is going to be 1/2 of the maximum force times delta T. Okay? And we just make them, both of them, the same. And we're going to solve for delta T. So delta T will be twice quantity mf mvi over f max. And then I'm just going to substitute values here. And I'm going to have 2 times 0.6 times 3 minus 0.6 negative 0.3 over 36. Your equation may look a little bit different, but more or less that's what you have. And this, I think you end up with 0.2 seconds. Okay, so this delta T, this lapse is going to be 0.2 seconds. Yeah, makes sense? Hallie? Yeah? Okay, so this is more or less the kind of problems that we can do right now. The most I can ask, or at this point, will be different shapes of your impulse graph, and either I can ask for the time, or I can ask for the maximum force. But that's pretty much it. Maybe instead of a triangle, you have like a semicircle, or you have a positive and negative values, or things like that. But most of them, they work with the same assumption. The graphs can be divided in sections that based on basic geometric figures that you can calculate the area pretty easy. And then you just find what is the change in momentum on the other side, and then you just solve for the unknown variable. But that's pretty much it. We're gonna do more on Friday, but right now I want to stop here and go to the next topic. Okay, make sense? Okay, so so we're looking at this conservation of momentum. We're looking at this impulse momentum equation. But imagine that you have an event like a collision or an explosion that involves either forces that are really big or times that are really, really short. So if you have, for example, 2 football players that they are hitting against each other and then they crash, then they're gonna smash each other for a little bit, and then they're gonna bounce off each other. And you're gonna have an initial velocity here, and you're gonna have a final velocity So what's happening here at, at that collision is really hard to measure. So using the impulse momentum theory is very complicated because we don't have the forces and we don't have the times, and they're really hard to measure just because the nature of the phenomena is too fast and too violent. This can be the collision of two people, it can be a crash between cars, it can be collision between molecules, it can be a gas being heated. You can have these kind of collisions and they're really hard to evaluate. But the thing is that what we want to know is that if we have the initial conditions of the event and we predict what's going to happen later, that's what we want to know. Can we do that without knowing what's going in the middle? And so what we're going to do is we're going to apply Newton's third law. And Newton's third law basically says for every force, there's going to be an equal force but in opposite direction. So if you are pushing something, if you're pushing the wall is going to push you back with the same force, just in opposite direction. Okay, so this will be Newton's third law. Okay, so I'm going to look at what's going on my mass number one, on my first player. So I'm going to have a mass one that is moving to the right, and then at one point it crashes with something, and then it bounces off in the opposite direction. So here I can calculate an initial velocity, and I can measure a final velocity. I know that here there's going to be an amplitude, there's going to be an impulse. And the impulse, I'm going to call it impulse one. I don't know anything about that impulse. I don't know what is the magnitude, I don't know what is the amount of the forces, I don't know how fast or how slow is that collision, but I know that there's going to be an impulse. And I know that there's going to be an impulse because the velocity changed. And I know that if there's a change in velocity, if there's a change in momentum, there has to be an impulse. Okay. Now I'm going to look at my second mass, and I'm going to have my second mass going with an initial velocity is going to crash, or something's going to happen to it, and then I'm going to have a final velocity and the ball moving in a different direction. Okay, again, I know that here at this collision, at this point, because the momentum of mass number two is changing, there has to be an impulse. Okay, and I don't know anything about that impulse, but what I know is that if there's a force one here, there's going to be a force two here, and there has to be equals but in opposite direction. And I also know that whatever time the collision happened is going to be the same time for both particles. So the impulse of one is going to be the opposite of the impulse of two. So J1 is going to be equals to minus J2. Okay, so now we can try to get something. So I'm going to have that J1 is going to be equals to the change in momentum of particle 1, and J2 is going to be equals to the change in momentum on particle 2. But I know that J1 is going to be negative J2, so the change in momentum in 1 is going to be equals to negative the change in momentum in 2. Okay, and now what I'm gonna do is I'm gonna write those momentums in terms of masses and velocity. So the change in momentum in one is gonna be mass one, final velocity of one, minus mass one, initial velocity of one. Okay, and for the second momentum, I'm going to have the negative of everything. So I'm going to have negative m2 bf2 plus m2 di2. Okay, so it seems just like a little bit of algebra, and basically that's what I'm doing. But what I'm basically doing is I'm looking at the changes in velocities of two particles without looking at the forces and time of interaction between the two of them. Okay, so I got rid of any information about the forces. I got rid of any variable depending on the time, and I have this impulse theorem equation just written in the terms of the interaction of two particles in terms of their masses and velocities. So basically I'm saying I really don't care what happened in the middle. If I know the initial conditions, I can find the initial conditions regardless of what happened here. I don't care what the impulses are. If I have enough information, I can predict the behavior of all particles. Right now, I'm doing it with just two particles, but this can be applied to 3, 4, or n number of particles. I'm working with one axis, and for most part, we're going to be doing just one axis, but this can be working 2 dimensions or 3 dimensions, okay? Now, on one side of the equations, I have the momentums of particle 1. In the other side of the equation, I have the momentums of particle 2. What I'm going to do now is that everything that involves initial conditions, I'm going to put it in one side of the equation, and everything that involves final conditions, I'm going to put it in the other side of the equation. So I'm going to put all the initial velocities here and all the final velocities here, okay? So this is just rearranging variables. So I'm going to have m1 bf1 plus m2 bf2 equals m1 bi1 plus m2 bi2. Okay, so this is the final momentum. This is the initial momentum. Yeah, so everything that is on the right depends on the initial conditions. These are the final conditions. Okay, and this is the conservation of momentum. And this one is a really big deal. This is one of those basic laws of physics that you're always gonna see it. You're always gonna it's always gonna be valid. It doesn't matter if you are working with very small masses like molecules or atoms, or you are working with huge masses like asteroids, planets, galaxies. You're always gonna have that law being valid in all conditions. You're always going to have conservation of momentum. So this is one of the big ones. Conservation of momentum basically says that if I know the initial momentum that I have, whatever the momentum I have at the initial conditions, this momentum, regardless of what happens in the middle, has to be conserved. No matter what, you're always going to have the same momentum at the beginning and at the end. Okay, and this helps us to understand a lot of phenomena like recoils and explosions and other kind of things, like how a bullet smashes the bones in the head. Alexis, you got really That I caught your attention with that example.
Yeah.
Yeah, there's actually a problem involving that. So in ballistics, something that you can try to do is, okay, when they're trying to reconstruct crime scenes, what they can do is look at the location of different fragments of bones, and by looking at the location and the masses, they can predict, well, where was the initial impact, and it's just by conservation momentum. When there are explosions of rockets or airplanes and the airplanes explode in the air, you can trace the different parts, the different masses, and you can see where the plane was coming and where it was going just by conservation momentum, because physics, science, I don't know. Okay, so we're gonna do a couple of problems just with conservation momentum. Okay, we'll do the example of the head just for you. Just maybe not today, maybe Friday. Simple case, you guys like sledding in winter? Yeah? I've never done it, so I have no idea. Is it fun? Would you recommend? Okay, I'll try this year. If I break my back, I will blame you. So, when was the last time you went to Makina? When was the last time you were in a sled?
During quarantine, we got a new golf cart, and me, my brother, and my sister went sledding. There was no snow; it was just on straight dirt.
So you just got pulled by
A golf cart.
a golf cart? I don't know how to put that here. Okay. There is. Do you used to have long hair when you were a kid?
Did I have one here?
Uh-huh.
Yeah.
Okay. So there's Makina. That's the ponytail. She's running in the snow, and there's a sled. Okay. So she's running. I'm gonna assume that the mass. She's a kid, so I'm gonna assume that the mass is 30 kilograms, and she's running as fast as she can. So she's gonna be running at 4 meters per second. Okay. She's running towards the sled. She's gonna be jumping on the sled, and then she's gonna travel on top of the sled. Okay. The sled has a mass of 10 kilograms. It's a big sled. And is standing still. So the velocity of the sled is going to be 0 meters per second. Okay. She's going to jump, and she's going to land on the sled. Okay. And the sled and her are going to be traveling together at some velocity that we don't know. And that's what we want to find out. Okay, so I don't know what's going on here in the middle. I don't know if she jumped and do a somersault. I don't know if she just threw around, or she was just a simple jump. I don't know, and I don't care. Like, the only thing that I care is what is the initial conditions and what are the final conditions. Okay, I don't know, and it doesn't matter what happens here. Whatever momentum I have here in the before, whatever momentum I have here, it has to be the same momentum in the after. Okay, so when you are working with these kind of problems, so when we are doing what we're going to be doing when we're talking about conservation of momentum and conservation of energy and these kind of problems, we're going to be looking at the before and after. What are our initial conditions and what are our final conditions? So here in the before, I'm gonna have the momentum of the person, of this kid, and I'm gonna have the momentum of the sled. And I'm gonna add those two momentums, and that's gonna be the momentum of the system. And whatever happens to that system, the momentum has to conserve. Okay, so I'm just gonna write the equations of conservation of momentum. So I'm gonna have m1 v1 initial plus m2 v2 initial. It's gonna be equals to m1 v1 final plus m2 v2 final. Okay. Kennedy, how are you doing? So what would be the momentum of the sled, the initial momentum of the sled?
0,
Why?
because it's not going anywhere.
Are you sure?
Yes,
Really, really sure?
yes.
Yes. So we don't have any momentum. That sled doesn't have any momentum. Okay? If you have a mass and that mass is moving, you will have momentum. So it doesn't matter how small the mass, doesn't matter how small the velocity, as long as you have those two conditions, you will have momentum. Okay? Now, I don't know. So this one is tricky. So how is the velocity of the sled with compared to the velocity of the person, of the kid? Is it bigger? Is it smaller?
In
In the after, yeah.
I treated it as the same,
Why?
because I saw them moving together, so.
Yeah, pretty much. Even though the problem doesn't say, or well, you can assume that if the kid is sliding on the sled and the kid are going to have the same velocity. So the final velocity of 1 and the final velocity of 2 are going to be the same. So we can rewrite this part and say, well, the two velocities are going to be the same. So this is just going to be final velocity times quantity m1 plus m2. And on the right side, because we don't have a momentum on the sled, it's just going to be m1 initial velocity of 1. Okay? I'm just having the momentum of the initial conditions have to be equal to the momentum at the end. And from here, I can solve for the final velocity. So final velocity will be m1 this will be 30 plus 30 plus 10 times 4. There? Any questions? No? Okay. So let's do one more problem and then I'm gonna let you guys go. Let's make it difficult so it's worth it. Like make you suffer and it gives you that sense of accomplishment. Mary just look at me like, shut up. Okay, something, okay. Ah, I know. So you have a bullet and the bullet has a mass of 20 grams. Okay, and it's traveling at a velocity of 300 meters per second. And you're gonna be hunting. And you're gonna be hunting turkeys. Is it turkey season? Soon, right?
Yeah, I think so.
You hunt?
It's usually, yeah.
You hunt turkey? Oh. I mean, I'm guessing because it's Thanksgiving, people hunt turkeys, right? I don't know. Okay, so you are hunting a turkey. The turkey has a mass of 20 pounds. So that's 10 kilograms. And the turkey is walking. He has no idea that he's being hunted. He's just walking. He has an initial velocity of 1 meter per second, minding his own business. Yes, looking for turkey babies or poor turkey. You hit the turkey, and the bullet. So now the turkey is going to be dead. Blood. Blood, blood, blood. The bullet comes out to the other side of the turkey, and now the bullet has a final velocity of 100 meters per second. Okay? It has the same mass. And I want to know what will be the velocity of the turkey. So you can imagine that the bullet hits the turkey and the turkey just keeps rolling forward. Think about this next time you eat turkey on Thanksgiving. Or you hunt.
Good.
It's good if you're not the turkey. So same thing. Look at the initial conditions, look at the final conditions. And those are the only thing that we care. We really don't care what's going on in the middle. We don't care about the guilt that the hunters may have or the relationship that the turkey just killed, just never had that closure. I think I shouldn't be taping these, recording these sessions when I'm doing this kind of examples. I think it's gonna come back in the point. Oh, that's supposed to be the eye, not the. It's not a bullet hole. It's the eye.
I know, that's how I was feeling. That's
Oh, yeah. What's the better?
I didn't want to come here, so. Drop off. Huh? Just drop off. Yeah, you're tripping. And Hallie's freezing.
That wasn't too fast. Just, oh, yes. I don't know. I don't know. Let's go because the turkey will be like super fast. I guess.
Casey, can I see your answer? Casey. You can write it down on the chat.
Sorry, I
cannot
was muted.
see.
I don't have the exact answer yet. When I get the answer from my, because I just have the equation set up.
Okay. Okay. Sorry for interrupting. Okay, so in this case, again, we cannot simplify many of the questions. All objects are going to have initial and final momentum. So one of the things that you have to be careful with working on these kind of problems is to keep track of which one is. Can't you not sleeping? You're falling asleep.
Yeah, that's what that's for.
But just 10 more minutes. Keep track of what are the initial and final velocities. Keep track of what are your masses. It's really easy to start mixing them. So I'm going to have initial velocity of mass 1. So these are going to be my initial conditions. And these are going to be my final conditions. Okay. So here I'm going to have 20 grams, 0.02 kilograms. The initial velocity is going to be 300 meters per second. For the second mass, I'm going to have 10 kilograms and 1 meter per second. And for the final conditions, I'm going to have same mass. Now the velocity is going to be a third. And then I'm going to have the same mass and then the final velocity. But that's what I want to find out. Okay. And then solving, there are different ways that you can solve it, but I think the easier one is just multiplying this. So here you're going to end up with 10 kilograms per second. On the first part, what you guys got? Alexis? 6? 6 kilograms per second. And here would you have 2 kilograms per second plus 10 BF. So this will give you 16 kilograms per second equals 2 plus this thing. So 14 kilograms per second equals 10 BF, and BF will be 1.4 meters per second. Okay. Yeah. Right now we have all the velocities going in the same direction. We're going to do a couple more problems where there's a recoil, and you will see that there's a collision, and then you can have objects bouncing off the object, and we can do some problems involving involving 2 dimensions. Okay, Emma, any questions? Are we ready to go? Shall we go? We still have 5 more minutes. 7. Shall we stay? No? You don't like my class? I'm working hard to prepare the class. You don't like it? Nobody likes my class. Okay, guys. Have a good day. See you on Friday. Okay, Friday. Mary, you're gonna teach class on Friday?
Yeah.
Okay, can be what, biochemistry or macrobiology. Okay, we're gonna have a macrobiology class on Wednesday, Friday.
Yeah, so it should be able to. Yeah, biochemistry, I didn't say.
I'm okay